Programmatic advertising is about bidding.
Optimal bidding is a solved problem.
Well, if your forecast is good enough.
You could always adapt.
How are we accounting for the fact we adapt again?
Well, we are not. It would become an intractable stochastic problem.
Maybe AI could help.
Let's
Let's
try.
try.
How does real-time bidding work? Suppose you get a user visiting a website. The website sends pieces of information, for example the device type, to the supply-side platform in order to create an ad request sent to an ad exchange. A bid request is then sent to various demand-side platforms so they can bid back. Bids are then sorted by the ad exchange, and the highest bid wins the impression. The winner can then display the ad to the user and pays for the impression according to the auction rule, with all of this happening in a few milliseconds. A publisher and an advertiser can agree on a contract to deliver a specific number of impressions within a given period of time, subject to penalties for not reaching target impressions. The publisher must set up an optimal bidding strategy to buy impressions. The overall cost of the campaign is then the spend on impressions and any penalty paid for missing the target. So suppose you target 100 impressions by the end of the day. You'll start bidding at a given level, buying impressions for an expected cost. By adjusting the bid level to the market condition until the end of the campaign, it is possible to reduce the cost. An optimal bidding strategy would choose the bid based on the whole history of the campaign. As this is untractable, the bid has to be chosen based on a learned state. This state is an approximation of all past events, a compressed memory, aimed specifically to keep relevant past information. In our approach, the state representation is provided by means of a recurrent neural network, updated based on the very last observations. The model has three different levels. At the top, the prediction of the bid from the recurrent neural network state. At the intermediate level, the update of the RNN state from the observed history. At the bottom level, the training of the recurrent neural network, which is a kind of meta-learning, as you learn a model that maintains a good representation of past events in order to achieve your optimal bidding strategy. A very important feature of our solution is the anticipation of under-delivery risk. The usual controllers adapt themselves to market variation, for example a drop in the available volume, by increasing their bids, which can occur at an important cost. But our controller would anticipate potential drops in the market by buying some impressions in advance, so if a market drop occurs, it can adapt easily and for a cheaper price. The more the controller anticipates risk, the higher it starts bidding, and the easier it absorbs shock in the available volume. This obviously entails a higher spend when the risk does not materialize. However, the more risk was anticipated by a model through its training, the lower the final spend and penalty are when risk does realize. Of course, drop does not necessarily occur, but in expectation, a carefully trained controller will have a smaller cost.